Alright, here's another example problem in projectile motion. What we want to do in this problem is we actually want to stand on a cliff and we are going to throw straight out initial velocity of, let's say, 10 meters per second. We're going to throw a projectile straight out and we're standing on a 100-meter cliff. What we want to know is how long is the projectile in the air? How far away does it land? We need to look at what we know and what we have. Now, an important thing whenever you're standing on a building, throwing something or dropping things off buildings, is it's best to put your origin at the corner of wherever that is. This is like our 0, 0. So in the x direction, x initial equals 0, but y initial equals 100. And then, of course, our gravity is working straight down. The other thing we know is somewhere out, we don't know where, we don't know x final, but we do know that y final equals 0. So we have this stuff, we have this much going for us. And we also know that this is v x initial is the 10 meters per second, vy initial equals 0 meters per second. So these are all the things we know, so we have so much information to work with. This is great. And we know that our projectile will move in the x at some constant rate, but because it's coming down in the y, we bring those two together and it's going to land somewhere, we don't know where, but it'll land somewhere out there. In order to figure out how long the projectile's in the air for, we can think about the fact that this is like mapping a projectile flying straight out and then dropping something, because Vy is 0, so it's like essentially it's being dropped. So how much time do we get if we're dropping something before it reaches the ground? Well, we can use the fact that y final is y initial plus vyi delta t plus 1/2 ay delta t squared. So we know y final is equal to 0, y initial is 100, we know that that term is 0, and then we have minus 1/2 of our 9.8 times delta t squared. We can solve this because this is minus 100 equals negative 4.9 delta t squared. Or delta t squared equals negative 100 divided by 4.9. And then when we can take the square root and these two negatives will cancel. And delta t is the square root of 100 over 4.9, which looks like it's going to be, so let's pull out our calculator and see what we get. Yep, 4.5. So it takes 4.5 seconds for our object to reach the ground. Now the nice thing is once you know the time is the same for both, 4.5 seconds. How far away does it land? Well, we can just use the fact that x final is x initial plus vx initial delta t. Well, and then there's plus the 1/2 ax delta t squared, but ax is 0, so x final is 0 plus our 10 meters per second we threw it at, times our delta t of 4.5 seconds plus 0, so x final is equal to 45 meters. So it should land 45 meters away when we throw it off this cliff. So one of the things we notice, and a good takeaway from this problem, is that if you launch something horizontally straight out, which is the definition of horizontal, it's a redundant statement, the only time you have in flight is however long it takes to fall to the ground. Because this y part is the free fall time, and that dictates how much time the projectile has in the air. As we change this height, that changes how much time we have in the air when a projectile is launched horizontally. And then just the time times the initial velocity tells us how far away it will land.